Welcome back to the Integrate Intelligently podcast, season 2, episode 18. I'm your host, Jeff Brickler, and today, once again, we're going to continue our web series on design for manufacturing with founder and CEO of CAD Talk Software, Scott Brickler. So before we jump in, I want to ask everyone here, if you haven't subscribed to the podcast, you haven't left a comment, or you haven't reached out to me or Scott on LinkedIn, I encourage you to do so. You know, we only can grow this channel, can only help improve manufacturing with your help to spread the word. So if you haven't already, please subscribe here on YouTube or on your favorite podcast platform, and that'll help, and share it with anyone else in your organization. So Scott, welcome back, and looking forward to, part 3 in our series of design for manufacturing. How's it been going? What's going on?
Oh no, it's been like I said, it's been a hot summer so far, and we're enjoying it nonetheless, and getting ready to go on a cruise with the family next month in August, and looking forward to this conversation today about how DFM mistakes, which is going to be pretty interesting. I'm sure there's a lot of them.
Yeah. So first 2 episodes, if you haven't listened to those, go back and listen to those episodes where we talked about DFM, design for manufacturing fundamentals, like 101, right? Intro to design for manufacturing. 102, if you will, episode part 2 was really around implementation, getting your engineers on board, what it might look like for a design for manufacturing approach. And today we're going to go a bit deeper into mistakes, right? DFM mistakes, or design for manufacturing mistakes, and how to kind of, deal with those, manage those, fix them, that sort of thing. So just as a reminder, right? If you haven't been listening to this web series on DFM, design for manufacturing, the concept that during design stage by design engineers, they would take into account how a part is manufactured, right? We talked about, Scott mentioned in the last few episodes about optimizations, and design for manufacturing is one avenue of optimization for designing a product. So Scott, tell me a little bit about my mistakes. So maybe start off with a story around a mistake that you experienced in manufacturing, and how mistakes affect manufacturing companies, and what ends up happening.
Oh yeah. I think that, trying to think of an exact example. Because it's been a while since I've been actually in a manufacturing company, but I think there are cases, I've seen cases where engineers, they're designing things that aren't manufacturable. They're and that's I think I mentioned this in a couple episodes ago too, is that it is possible in a CAD system to design something from which it would be prohibitively expensive or impossible to actually make it. Now it's getting more and more capable with 3D printing and things like that, where you can make things that are really kind of wild. But, when you think about material removal type of processes like mills and lasers and things like that, where you're cutting material away, there is possibility of creating things that you just cannot make. You can design them, but you can't make them. So that's typically that would typically be the biggest mistake that you could see. And you don't see a lot of that, but nonetheless, you do still see that, because you think about how a lot of times how an engineer designs something, there's kind of 2 different ways they start with it. One would be they actually simulate how you'd make it by extruding a block and then cutting it away and then so it's kind of simulating what a machine would do, at least roughly, when you design it. But you could also design something, it's called they think it's a blob type of approach, where you just start with a blob and kind of move it around until and mold it into what you want. And it just depends on how they designed it. They can do that. And the second approach tends to create things that are, my experience has been that the second approach tends to make things that aren't really makeable, that are not really buildable. And that's typically the thing. The other mistakes you get is things that are just really difficult to assemble, or they weren't thought out through. I gotta hang this wire harness on the back of the machine, and I can't reach the screws on the back with nuts to put the screw. I can't get there from here, right? It's just so it takes, what would be a 1-man job into a 2-man job with walkie talkies in order to put this thing together. I mean, it's it's ridiculous, right? So you just get into those types of things that are oh, yes, in virtual space, I could just put that together really easy, but on the actual ground with a 2,000-pound machine, I just can't spin the machine around and look at the bottom. I can't do that. It's I think a couple episodes ago, you talked about working on a car, right? Things that are just they were easy to assemble on the computer, but very difficult to actually do in production. And I usually see that around assembly. of things, because like, as opposed to like the machining itself. So it's possible to put it together. It's just going to be stupidly hard, things like that. So because once again, they're optimizing on multiple things. They design something and they may go and get tunnel vision and try to think, how can I eke the most cost out of this? Or how could I make this, where we only have to bend it out of one piece of metal, or, whatever. And then they just kind of create a situation where it's just like difficult to work with the thing, or just you can't assemble it, or things like that. Those are typically the areas where we see mistakes.
Yeah, I think of two things. You were mentioning I tie everything back to like my own experience of when we were kids, of course, working on the car, but also I think about like just simple stuff like the bolt holes don't line up, right? Like the really simple stuff like, hey, because if you're on the shop floor, right, and they're cutting this or they're drilling the holes or milling it or whatever, they're doing the work, and then comes the shop floor and it's like, okay, assemble this thing. And they're like, well, these things don't line up, man. Like, show me on the drawing and the model how these things line up. And the engineer will go, well, it lines up for me, or, or something that you didn't think about. Or like, yeah, it lines up. But to your point, like, there's a nut that goes on the back of this. Where am I going to get that? How am I going to put that nut on there?
Oh, yeah. I mean, good example, like that transmission thing that we talked about when we were kids. Like think about like lining up holes on two heavy things. So you have two heavy things in space that you're trying to align, and like you can do it in CAD easily. You just say line this hole, that hole, it just does it, right? But like in actuality, when you're holding an engine and then you're holding a transmission, and they're both heavy, and like the ones, and then how do you get those things in line to make that hole line up? Well, a design for manufacturing principle would be like using like a kind of a pinning type of thing, where you actually have a guide, kind of a pin that's rounded, and then you have a hole. So this heavy thing and this heavy thing kind of gets guided into that receiver, and you get that hole, right? And then it doesn't actually fasten it together. It's just a guide pin,
right,
to align everything. Then you could put the bolts in, right? And then so that would be a design for manufacturing thing that people added. Like, I can't really align these two things very easily without some kind of guide pin to do that, because they're both heavy. And things like that. And you see that in construction too, when you're like putting in these big beams and things like that. They tend to have like, say you're putting in a big like girder for a building, right? They don't like put holes in the bottom. They try to get the holes to line up with a big girder and then put the bolts in. They actually design it with the bolts coming out. Then they that's staying stationary. And then they take the girder and they lower it down over the bolts, and the bolts align into the holes, and then they put the nuts on. Because it's easier to do that than try to thread bolts through two heavy things.
Right.
It's just little things like that you think about when you're actually building it, what it would take to make it easier. Yeah. Like, and there's just thousands of those like variations and, principles that you use. There's other ones like design for gravity, like use gravity to your advantage. Like that's a very common engineering thing. It's like, well, if you're fighting against gravity, then you're going to tend to be more difficult. If you can work with gravity, you can do the same thing. So like, say you're putting bolts in the bottom and pushing them up against gravity, or putting them in the top and letting gravity align them. Saying like there's all different kinds of things you can do where you're designing around the fact that like using gravity to your advantage and things like these are all kind of cool little tricks that you think about that, incorporating, the real world into your design philosophy.
Yeah. Like it's not, not just alignment, but also like you said, like material types you choose, right? Like, hey, I think you mentioned on a previous episode about bend radiuses, like, hey, what material you use matters, right? Like we can't even bend that thing, the radius you have. Like we don't have that capability. So then you end up having to spend more money to create some kind of tooling or outsource it just to have that done.
Mm-hmm. Well, I mean, think about like if you were trying to create like a straight right angle, like you could design it something with a straight right angle, right? Or without any radius in it. Right. If you designed it that way and you had it had to be that way, you'd probably have to mill it. You'd have to take a block of metal and then mill it out an angle from it. Or you go buy angle. You buy angle too, just buy out the shelf. But you have to mill it out to create that same effect. Right. And then you're like, well, do you care about that being a straight edge, or it's just easier to design that way because, it started that way and you didn't put that. But if you design the bend radius, then you know that you could form it. And that forming could be it's going to take a lot less time, a lot less cost than cutting away all the material. It's a very rudimentary example, but it's the idea of that, like you can just by not putting a chamfer or not putting a bend radius on it, you're kind of deciding that at the design stage, is it going to be formed or not? And you might say, well, my tolerances are too tight. Like forming only has, a certain amount of tolerances it can hit. with a press brake, but I need this thing to be really tight because it's going to be in a slot gauge or whatever, it's going to be in a channel that's not, whatever that is. And you have to do it the way you have to do it, right? Because it has to work. So there's all these are all the constraints that you're dealing with and things you're thinking about when you're designing.
Yeah, that's a good point. I was thinking about like lead times, right? Like sometimes choosing a part that you need to purchase, the lead time matters, right? Like it's not the only thing that would be the decision maker, right? You might need to select from a number of different parts based upon lead times, based upon what'll work, right? You need more information. Otherwise, you could design a part and go, I designed this part and we need to get this special part and I can only get it from this one supplier. I mean, we actually have this in semiconductors where like, this is something that like you hear a lot about now, especially given all the rhetoric around semiconductors and AI, but like how like there's the Dutch make a certain machine that is like was it ultraviolet. It's a special machine the Dutch this Dutch company makes that allows us to make the really thin chips. Not us, but like, manufacturers make the really thin chips and only like that manufacturer does it. And then like only certain manufacturers have like that like capabilities to do those things. And so designing for manufacturing can often like cause these situations, right? Where you get sort of bottlenecked into like one supplier and then like anything goes wrong with that supplier, or anything goes wrong at all, you're hosed.
Yeah. Yeah. Because they've optimized where like the number of people who can supply that optimization is lower. And then you end up having kind of the example we had from a couple episodes ago about supply chain, where you have trucks like that need a single chip to be made in order to come up with the assembly line, because you have a single source supply chain issue. And that single source goes out, then your supply chain is disrupted, and I predict that you'll see more design for manufacturing incorporate more supply chain constraints than ever because of recent things with COVID and other things that have happened, that being resilient to supply chain disruption will be a factor of design for manufacturing in the future.
Yeah. I mean, I've already seen some of the platforms that we work with coming out with supply chain modules, if you will, right? Things, other capabilities to help with supply chains, right? To be able to pivot and make better supply chain decisions. And that's going to be needed all the way back into engineering, right? Even if you have better supply chain information in one system, if you're not designing with that in mind, you're not going to know about it. And you're going to continue to do the same kind of, hey, I designed this is how it needs to be made. Go figure out how to make it.
Oh yeah. Yeah. And I think about like some of the capabilities of the future. If there's all kinds of like compromise you can make to deal with supply chain issues. I mean, I think an example I've used in the past with the previous episodes talks about different finishes on stainless, right? You have number 3 stainless, number 4 stainless. Number 4 stainless is just a polish on both sides, and number 3 stainless is a polish on one side. But if you had a part that you had specified only needed number 3, you could technically make it a number 4, but you couldn't make a part out of number 3 that's specified as number 4 out of number 3 because both sides aren't polished, right? But like from an optimization standpoint, you're like, well, if I have number 4, then I can go ahead and make parts out of number 3. It's going to cost a little bit more, but at least I have it, right? And then and that kind of game time decision making on the shop floor, I can see that being more and more of a thing where we're like, we do material substitutions based on supply chain and based on those optimization problems, and running those kind of algorithms to figure out how to optimize real time based on what is available, how quickly do I need it, all of those things being kind of done automatically, especially within a world of AI.
Sure. Yeah. Make even faster decisions all throughout, right? The whole process from the design phase all the way to the shipping out the door, right? So that you can do that with fewer mistakes, faster, cheaper, all of those things. So like in terms of design for manufacturing, and like to avoid those mistakes, really, what are some things that like a design engineer, like what's kind of the framework or thought process that person would need to have?
I think you always got to have a reality check when you're designing of like, can I actually build this thing, and can I, and what would it be like? Can you visualize how you would do it if you were that person? If you were assembling it or you were making it, think about how you're going to do the thing. You may not be as a manufacturing engineer, but you have a general sense as an engineer kind of how things are made. and then having discussions around your capabilities in your shop and of your vendors and things like that is always good to have during the design phase, and then doing a spot check, and then just maybe bouncing. They also can do design reviews where you actually ask people, and your colleagues to look at your design and say, how easy is it to make this thing? Think about it. And I think those are all great principles to use anytime you're building something. And that's true of like any designing endeavor. We do the same thing with like code and with, any kind of engineering discipline. That's always going to be a really good process, a really good way to do it. And I think in the future, you're going to be able to ask AI to help you with that too.
Sure. Yeah. I mean, some systems are already starting to have that, right? Being able to some of the platforms we work with, use AI to help you make those decisions.
Absolutely. Yeah. I think you're going to see it's going to be a huge revolution of like AI assisted everything, right? But AI assisted design is definitely in the future.
Yeah. I would imagine AI assisted manufacturing, just like DFM, is going to be in the future too.
Absolutely.
Yeah. So, it's kind of a question, since I'm not an engineer myself, what you were focused on as an industrial engineer, which is kind of a person in the middle, right? Like, or a manufacturing engineer. That's kind of the role you've had in the past. And that made you closer to manufacturing. How much, when a design engineer goes to school and they get out and they start working if they were working at a manufacturing company, like, how much do they understand about manufacturing itself? Like, how much training is involved? Like, I mean, your company that you worked at when you started in manufacturing, they manufactured products, like in the shop floor. You went to that. But I would imagine some companies, right, the engineer may be a bit removed from the manufacturing process. How much knowledge of manufacturing does an engineer get in school, or how does he or she get that knowledge?
Yeah, I remember, I went to school, like you said, I went to school for industrial manufacturing engineering. So we actually got quite a bit. We learned about that. I think, typical mechanical or electrical engineers, probably more mechanical than electrical, has some knowledge around that. And I think some of it's just experience, right? If they work at a place that has, machining and things like that, they tend to have more, they'll get that experience pretty quickly, because their designs will get kicked back a lot. And, there's the iterative approach of like, this ain't going to work. We can't make this, type thing. Yeah. When they're starting out, they probably have I would say it's probably a similar knowledge that like a doctor would have about nutrition, right? They have the basics, but they're not going to be able to do much unless they really study it, right? And then you have to know the nuance of the companies and the capabilities that you have. But they generally know that like how certain things are made and, and the general principles around it, but they probably learn a lot from experience.
Well, Scott, this was another good conversation about Cat Talk, and well, not just Cat Talk, but really about the DFM, design for manufacturing. And I know, just a quick kind of plug here about, Cat Talk itself, in the sense that, we have a design for manufacturing module that helps get data out of ERP into manufacturing, into the designer's hands, right? At the time of design, to help make better decisions. So I would encourage everybody to, download our DFM PDF that you'll be able to find a link in the show notes here. Again, encourage you guys to subscribe to the podcast, give us a thumbs up, comment, listen, share internally. Feel free to connect with us on LinkedIn, both me and Scott. Again, another fair warning, if you look for me on LinkedIn, more than one Jeff Brickler, so make sure you get me. So look in the show notes for all that information. And Scott, just to preview our next episode, we're going to give them some practical examples, maybe using CAD Talk, or maybe just using what they have today, some of like how to implement some kind of DFM strategy, some kind of design for manufacturing strategies with their teams today, no cost, low cost, or just practical steps to be able to do that.
Awesome. Yeah, looking forward to it.
All right, Scott, that's all for us today. Thanks for the conversation.
All right, thanks. Thanks, everyone.